Hello to everyone, my name is Miguel García Tecedor, and today I would like to welcome to the first MOOC inside the HySolChem project regarding photoelectrocatalytic solar fuels production. So in this MOOC, we will start with a brief introduction of what is photoelectrocatalysis. Then we will start with the fabrication of a copper bismutate photocathode that we will use as an example for this application. And then we will start explaining some basic principles in photoelectrocatalysis. So basically what we try to do is mimic natural photosynthesis in a process called artificial photosynthesis, where we try to use abundant molecules as CO2, nitrogen, or water, and convert them by using solar energy into solar fuels. In that sense, being able to store the solar energy into chemical bonds. So why copper-based materials? So as you can see here, there are many different copper-based materials that has a good favorable energy imbine alignment to different interesting chemical reactions. So basically we employ them because also they have a non-critical nature, they're inexpensive, they also have a favorable band energy alignment, as I commented, and they also have a promised selectivity, for example, towards C1 and C2 products, but they also produce hydrogen. And basically, it's true that they suffer from photocorrosion. But today we will employ one recent article that we have published in the framework of the HySolChem project regarding a copper bismutate photocathode for the hydrogen evolution reaction. So in the fabrication of this copper-based photocathode, all the details, of course, are here in the reference, but basically what we do is employing electrodeposition technique. So basically what we have is a soda lime glass covered with fluorine-doped tin oxide, which is a transparent conductive oxide, which is able to make conductive the glass without losing the transparency. And then what we do is introduce our substrate in the electrolyte, where we have the copper and the bismuth precursors in solution, and then we apply the negative potential, and then these cations get attached to the surface. And finally, this is the aspect of the fabricated photocathodes. So we basically quickly check by X-ray diffraction that we have the adequate crystalline phase, what is the tetragonal phase associated with copper bismutate. And then we start with the photoelectrocatalytic studies that is the interest of this first MOOC of HySolChem. So first of all, we measure the open circuit potential, which is basically the potential in equilibrium of the material and the electrolyte. And we do this measurement under chopped conditions, under chopped illumination, which is what we usually say. So basically, we are turning on and off the light and see the response of the OCP. And what we see is that we have a positive response of the open circuit potential under illumination, which is an indication of a p-type behavior of your semiconductor. And as it is well known, this material is a p-type semiconductor. We also measure the Jaeger response. And for doing that, we basically do a linear sweep voltammetry. So basically, we are scanning different potential windows while we are recording the current density. And we do that also under chopped illumination. And we can see here that this one should be the current in dark, and that one here is the current under illumination. And the difference is the photocurrent. So basically, we can see that in the copper bismutate, we have it's a photoactive material because it is a semiconductor. And it is also interesting that we can see that we have a higher current density under back illumination than under front illumination. And this, for doing that, we usually do this experiment, and for understanding that, we usually do this experiment under these two configurations, trying to understand a bit more regarding the mechanisms inside the photoelectrode, a photocathode in that case. So basically what happens when we do back illumination is that we photogenerate the electron and holes in this region close to the FTO. So then the photogenerated holes only need to travel this small way back to the FTO contact, while the photogenerated electrons need to travel all the whole thickness of the sample to arrive to the surface and then being able to reduce water into hydrogen. If we do front illumination, it happens the opposite. So we generate the carriers here, and in that case, the photogenerated holes need to travel all the thickness of the sample back to the FTO contact, and the electrons are very close to the surface to drive the hydrogen evolution reaction. So in that case that we have a better response because we have a higher current density, or the current density under back illumination, is because the diffusion of the photogenerated holes were the limiting factor in the performance of copper bismutate. If we now take a look to the response of this photocathode material in the presence of a sacrificial agent, we can now take a look to these two graphs here. First of all, we have cyclic voltammetry, and here we have the same linear sweep voltammetry under chopped illumination. First of all, a sacrificial agent is a substance that it's very easily reduced or oxidized. Sometimes it's also called hole scavenger or electron scavenger, depending if it's for oxidation or for reduction. But basically, it's something that it's, as I commented, very easily oxidized or reduced, and then we are able to remove the diffusion limitations in our photoelectrode. So for this purpose, we add a bit of hydrogen peroxide to our potassium phosphate buffer, and which is acting as an electron scavenger, the hydrogen peroxide, and we can see that we are able to improve the performance of our photocathode. So basically here, we employed a cyclic voltammetry as an indirect measurement of the stability. Here we have 3 cycles, under dark and under light, and we can see that all the cycles have the same shape. We don't have hysteresis, and we are not losing any current. So basically, we can see that our material is being stable in the presence of these solutions. And this difference is also the photocurrent density. So if we now take a look to the JB response under chopped illumination, we have compared here the performance of the bare copper bismutate in potassium phosphate, which are the same result that I showed you in the previous slide, and in the potassium phosphate plus hydrogen peroxide. And then we can see that we were able to have around 3 times higher photocurrent density in the presence of higher hydrogen peroxide. And this is an indirect measurement that we can use to know that we have a higher room to improve our material. So that for doing that, we deposit a silver co-catalyst, trying to see what was the performance of this improved photocathode. So then we deposit the silver nanocorals on top, and then we see that this is also in bare potassium phosphate buffer, that we were able to improve a bit the photocurrent density by using the co-catalyst, since the co-catalyst is mainly employed to drive faster the desired chemical reaction. So basically, the photogenerated electrons goes from in the surface of the copper bismutate, go to the silver nanocorals, and then they reduce water into hydrogen faster, right? But still, we have this spike these spikes that you can see here in the chopped photocurrent density, and these spikes are usually related with surface recombination. So if we now do both things, so we do this same experiment, but in the presence of potassium phosphate plus the hydrogen peroxide, now we can see that we're really able to improve the photocurrent density and also to reduce the surface recombination by using the sacrificial agent and also the co-catalyst. Usually these kind of experiments are employed to try to understand a bit more the mechanisms inside the photoelectrocatalysis of your semiconductors. And with that, I just would like to thank you very much for your kind attention. And if you want to know more about our project, here you have the webpage of HySolChem. And basically, thank you again. Bye-bye.